Hi everyone, welcome to another video of Calculus 1. In this video, I'm going to explain the derivatives of trigonometric functions. Derivatives of trigonometric functions. So first we take the derivatives of sine and cosine, then we're going to look at how we can generate the derivatives of other functions. Let's take d of d over dx sine of x is equal to cosine x. And then here actually y equals sine x and y equals cosine x are differentiable functions. That's why we can write this ex cosine x is equal to negative sine x. Of course, we can prove this going from first principles, limit differentials. But I'm not going to do this in this video. Perhaps in another video to show how this derived. Um, if you want to learn that, check out my other videos to find out the derivative, the proofs. But you can find the proofs in any textbook. Um, so we can write this because y equals sine x and y equals cosine x are differentiable functions. We learned that they are continuous functions as well in the limits. And let's see what other uh, functions that we can derive from this. Uh, Before that, I can compute a small problem example. I can do uh, f of x times cosine x. You can apply the product rule here. So I can write f prime x is equal to x times d over dx cosine x plus cosine x times d over dx x. Now using product rule, right? Remember the product rule that we used earlier. So this x, this is negative sine x plus cosine x times 1. So we have negative x sine x plus cosine x. This is f prime x. Uh, and let's see another one. How do we get this? D over dx tangent x. So we know that tangent x is equal to sine x over cosine x. So we can write that sine x over cosine x. We can use the quotient rule here, or we can use the combination of product rule and chain rule. I'm going to use the quotient rule here. So if I use the quotient rule, it's the function at the denominator cosine x times d over dx, the function in the numerator sine x minus uh, function in the numerator sine of x and the derivative of the function in the denominator divided by cosine x squared. And this is cosine x, d over dx sine x is cosine x minus sine x d over dx cosine x is minus negative sine x divided by cosine squared x. And now you on the numerator you have cosine squared x plus sine squared x divided by cosine squared x. So you have this is equal to 1 over cosine squared x. That means secant squared x, which is d over dx tangent x. Okay. And then the second one, d over dx secant x. I should be able to get this one easily because it's d over dx secant x is 1 over cosine x. Well, I can use the things that we learned in the chain rule here, d over dx. This is cosine x to the power negative 1. So we learned that d over dx gx to the power n is equal to n times g x to the power n minus 1 times g prime x. So here gx is cosine x. So I write uh, if I take gx is cosine x, I can write negative 1, right, to the cosine x to the power n is negative 1 minus 1, right, and then d over dx cosine x, right. So this is negative 1. Uh, you have cosine is x squared, so cosine x squared on the denominator, and then this is negative sine x. So you have negative sine x, negative 1 is sine x divided by cosine squared x or cosine x squared, both are the same. So this is, I just want to reiterate that I think I have mentioned that cosine x squared is equal to cosine squared x. And then sine x squared, usually we write sine squared x, right? And then sine x, we can write sine x divided by cosine x times 1 over cosine x. This is tangent x times secant x. So this is d over dx uh, secant x. So it's d over dx, usually we write it as d over dx secant x is equal to secant x times tangent x. Similarly, by taking similarly, you can do d over dx cotangent x, right? I can use the chain rule and product rule here. So I can write cotangent x is 1 over tangent x. That means cosine x divided by sine x. So I can write d over dx cosine x times sine x to the power negative 1, right? So then product rule, applying product rule, I can put sine x to the power negative 1 times d over dx cosine x plus cosine x times d over dx sine x to the power negative 1. So this is 1 over sine x. This is negative sine x plus cosine x. And here again we apply this rule d over dx g x to the power n is equal to n times g x to the power n minus 1 g prime x. Here we're going to apply that. So our gx is sine x here. So we have -1 sine x to the power -1 minus 1. That's this part. And then d over dx sine x, right? So this is -1, right? -1 and uh, negative co cosine x uh, over sine squared x times what this is cosine x. So it's cosine x squared sine x. Mm, this is -1 cosine x squared sine x squared. This is cosine x, that's right? So uh, we have -1. I take sine squared as my common denominator. Sine squared x. You have sine squared x minus cosine squared x, right? And you can take -1 out, then you get sine squared x plus cosine squared x divided by sine squared x. Sine squared x plus cosine squared x is equal to 1. So -1 divided by sine squared x, you get negative sine, negative cosecant squared x, right? And then the last one, you have d over dx cosecant x is equal to, I'm not going to show that, but you can do the same manner by taking cosecant x is 1 over sine x. You can take d over dx 1 over sine x, and you can use the same rules that we used before, and you can get negative cosecant x times cotangent x, right? So what we obtained so far is d over dx sine x equal cosine x, d over dx cosine x equal negative sine x. These two can be proved by using first principles, right? And the other four can be proved by knowing this. You can do d over dx tangent x is equal to secant squared x, d over dx cotangent x is equal to negative cosecant x, negative cosecant squared x, and d over dx uh, secant x is equal to secant x times tangent x, and d over dx cosecant x is equal to negative cosecant x times cotangent x, right? So these are the derivatives of trigonometric functions, and we can use the whatever the rules that we have learned so far to solve these problems. So let's solve 5 from the book. Um, we have good, question 5. F of x is equal to sine x times cosine x. So f prime of x is equal to, you can put the product rule, uh, d over sine x times d over dx cosine x plus cosine x times d over dx sine x. So this is sine x negative sine x plus cosine x is cosine x. So you have sine negative sine squared x plus cosine squared x. Um, you can use some trigonometric identities like it's negative sine squared x plus 1 minus sine squared x. So you can put 1 minus 2 sine squared x for uh, f prime x. And you can use number 12, book 12. K of theta is equal theta squared times sine squared theta. So we can write dk d theta, which is equal to theta squared d over d theta sine squared theta plus sine squared theta times d over d theta theta squared. So we have theta squared here. Now we learned that what happened when you have something like this, d over dx gx to the power n is equal to n times gx to the power n minus 1 times g prime x, right? So here in this case, g theta, which is actually sine theta, so you can write 2 times, right? Uh, Sine theta to the power 2 minus 1, right? 2 minus 1 times d over d theta sine theta plus sine squared theta times d over d theta theta squared. So I can write in terms of, I can use this equation, d over dx x to the power n, so it's n x minus 1. So you can write 2 times theta 2 minus 1 to the power 2 minus 1. So you have theta squared. This is 2 times sine theta, and d over d theta sine theta is cosine theta plus 2 times sine squared theta, and the 2 minus 1 is theta, 2 theta times sine squared theta, right? And we have 2, you can take 2 theta out, sine theta out as a common factor. So then you have theta cosine theta plus sine theta. So that's our solution. Uh, and we can do book 23. We can do book 23. F of theta is equal e to the power theta 5 sine theta minus 4 tangent theta. Um, we can write df over d theta is equal to, these can be considered as two functions. So I can write e to the power theta d over d theta 5 sine theta minus 4 tangent theta um, plus 5 sine theta minus 4 tangent theta uh, d over d theta e to the power theta. So you have e to the power theta, and you can use sum rule d over d theta, and also you can use the constant multiple rule. 5 you can take it out, sine theta minus 4 times d over d theta tangent theta plus 5 sine theta minus 4 tangent theta plus d e theta, e to the power theta, e to the power theta 5 times cosine theta minus, for tangent theta is secant squared theta. We obtained that before. 4 times secant squared theta plus 5 sine theta minus 4 tangent theta e to the power theta. So e to the power theta is a common factor. You can take it out, and then you have 5 cosine theta minus 4 secant squared theta uh, plus 5 sine theta minus 4 tangent theta. Uh, I don't think that we can simplify further by going this way. You can write everything in sine and cosine, and then you put a cosine squared as a common denominator, and then you get cosine squared here. Now, I don't think that we can solve any longer, so I'll just keep it like that. Um, so you can use whatever the things that we learned before to solve any of these problems. Use along with chain rule, product rule, quotient rule, and also the derivatives that based on the chain rule, these equations and this one, um, we can solve most of the problems. Uh, well, that's all about the derivatives of trigonometric functions. I'll see you all in another video. Thank you very much.